Okay, ji, so this is the problem we are going to solve, and here we have to apply these two techniques. One of them is the Euler's method, and this is your improved Euler's method's formula, and you are provided here the differential equations along with the initial condition of y0 equals to 0. And further, you are given a few more informations, and you are required to work out within the range of 0 to 0.3 with an increment of 0.1. So this is the information provided in the question. Now, in order to understand this is the whole range of the interval in which we have to work out, and the starting point is 0 and 0 with an increment of 0.1. Let me show it on this straight line. This is your starting point, and we take start from 0, and next step will be at 0.1 by giving an increment of 0.1. Next is 0.2, and the last one is 0.3 due to this interval. So in order to move from this point to this point, we are using h equals to 0.1, and similarly everywhere h is equals to 0.1. Now further, we label this as x0, this as x1, x2, and x3. Okay, I show them on this side. x1 is equals to 0, x2 is equals to 0. This is x0 and x1, and x2 is equals to 0.2, and the last one is x3 equals to 0.3. Now the task is to find out the corresponding values of y. y0 is given from the initial condition, this is 0. y1 we have to calculate, y2 is unknown, again we have to calculate, and y3 is still unknown. So these are the three required values we are looking for, and for these values we'll be first apply the Euler's method, and then we'll be using the second method. Now you have to keep this data into your mind, and before proceeding, as I told you, in these methods, in order to find the next value, we have to use the previous value. So in order to go for y1, we have to use y0 and x0, and similarly we shall proceed on the same line. Now we one more thing, let me write it here for you. From the differential equation, if you compare it with the standard differential equation, and this is dy over dx equals to fxy, so on making the comparison, it is not difficult to say fxy is equals to 1 minus y. Okay, so I'll be using fxy over here in the form of 1 minus y. So after giving the whole detail or description of the question, now I'm going to erase it from here and start solving the identity process. Okay, now we use the first method, Euler's method. So to take start, first of all you have to write down the formula. The formula is still on the board. You can write it directly. Okay. The first iteration starts by putting m equals to 0. On putting m equals to 0, everywhere the index will change. 0, h, f of x0 and y0. And now you can see here y0 we have just seen there in the initial condition, that was 0, plus h is 0.1, and f of x0, y0 is 0 and 0. And keep it in your mind that fxy we have defined by using the standard differential equation. This was equals to 1 minus 1. Now on putting x0 and y0 over here, what do we get? 0.1 f of 0 and 0 gives you 1 minus 0, so the output is 0.1. So corresponding to the first unknown, we get y1 is equals to 0.1. This is your first unknown. On taking m equals to 1, the change will be m2 on the left side, y1 plus h times f of x1, y1. y1 is, we have just calculated, 0.1, plus h is the same, fx1 is 0.1, and y1 is 0.1. Okay, after putting the values into the formula, into the function, this is your function, taking x equals to 0.1, there is no x on the right side, there is y only, so we can put it 0.1. Now you can use your calculating devices, and on simplifying, the result is 0.19. So we got the second unknown y2 in the form of 0.19. Okay. I hope you are following and you can understand it. Okay. Now to proceed for the next, I am using this once again. Here we take m2. On the right side there will be y3. This will be y2, and these are also replaced by x2 and y2. Now y2 we have just calculated, that is 0.19 plus 0.1, f of x2 is 0.2 and y2 is 0.19. So this is the so far information. On putting the functions value in, so this gives you 1 minus 0.19 from here. Okay, now if you simplify it, the result gets equals to 0.271. I hope you can verify it of yourself, and if you find any flaw or any errors, so you can remove it of yourself. Okay, so this we obtained the that's fine. The three outputs for the case of the Euler's method. Now you can apply the improved Euler's method to obtain similarly three more results. Okay, so far this was the application of the first formula. Okay. The second is the use of this improved Euler's method. I'm not going to write once again the formula, this is still on the board. I'm just changing the index. The first iteration starts putting m equals to 0. So this gives you y1, y0, h by 2, f of x0, y0, f of x0 plus h, y0 plus h, f of x0 from here and from here y0. And now bring in the values. Y0 is 0, h is 0.1 by 2, f of x0 is 0, y0 is 0, 0 plus 0.1 for this quantity, and here we have 0 plus 0.1, f of 0 and 0. And we know that fxy is 1 minus y. It takes the form 1.1. This gives you 1 minus 0. From here, if we simplify, this is, there are two functions. So first we apply the inner function, this one. It gives you 0.1 outside, and inside this gives you 1 minus 0, like that. And further we get 1 by 2, 1 minus, this is 1 minus 0 gives you 1 plus f of 0.1, and from here we get 0.1. Now the outer function, whenever you apply, we get 1 by 2, 1 plus 1 minus 0.1. Okay. On simplifying and using your calculating devices, the result is equals to 0.095. So this is the result for the first iteration by putting m equals to 0. Kindly note it down, and now we are going to change the index here, and I'm going to erase it and calculate the next approximate value for y2. So here putting m equals to 1, sorry, on the right side this will be y2, y1, x1, y1, x1, y1, x1 and y1. Okay. After changing the index, now we put in the values. This is your y1. Now put in the values, we get y1 is